Very much. Thanks very much for the invitation. It's, of course, a great pleasure to be speaking here at IAS. So I'll be giving a counterexample to the Arnold conjecture in the C0 setting. So let me begin by stating a version of the Arnold conjecture. It doesn't really matter which version, but I should state at least one version of it. So let's go with the original version that Arnold himself stated. Let's take m omega to be closed symplectic, a closed symplectic manifold. And what Arnold conjectured was that the number of fixed points of a Hamiltonian diffeomorphism is bounded by some number crit of m. Here's its definition. It just depends on the topology of the manifold. It's the minimal number of critical points of a smooth function f. Okay, so and he conjectured this is true for all phi in Ham, group of Hamiltonian diffeomorphisms. Okay, so as I said, this is, usually in symplectic geometry we treat other versions of the Arnold conjecture, but this is the original version that he stated. And in case you were wondering in what generality it has been proven, here are some cases at least I know of. If M is a torus, then this was done in the famous paper by Conley and Zender. More generally, if you have a symplectically a spherical manifold, so suppose omega and the first term class vanish on pi 2, then this case was done by, so it's written down in the paper by Rudiak and Opria. And they built on earlier works of Floor and Hofer. And I think there is one other case. There's one other case that I know of. There's probably others. And that's the case of CPN. And this was done by Fortune and Weinstein. Okay, so other versions of the Arnold conjecture have been solved, proven in more general situations. And so as I said, here's the main result of the talk. And this is joint work with Lev Bohavsky and Vincent Millier. And so the statement is that the Arnold conjecture is not true for Hamiltonian homeomorphisms. Homeos. Okay, so this is not a very precise statement at this point. You're probably wondering, I need to tell you what Hamiltonian homeomorphisms are first, and that's what I'll do over the next 10 minutes, 10, 15 minutes or so, and then we'll see how badly the Arnold conjecture will fail too. So I'll make the statement precise in about 20 minutes or so, in case, my hope is that. Oh yeah, thanks. If dimension of M is bigger than or equal to 4. Yes, that's important. So the 4, I guess people can't see it here. So there's a 4 here. Okay, but the precise statement will come in about 20 minutes or so. Okay, so let me tell you first, I think a lot of people now know what symplectic homeomorphisms are, so I very quickly will give the definition of those, and then I'll move on to Hamiltonian homeomorphisms. So here's the theorem that kind of allows us to define symplectic homeomorphisms as the theorem of Ilyashberg and Gromov. So here's what it says. Suppose you have a sequence of symplectic diffeomorphisms. And let's assume that these maps converge uniformly to something that I call phi. So phi might be a homeomorphism, but let's suppose it's a diffeomorphism. And so people usually have trouble reading my if. If phi is a diffeomorphism, then what these guys proved is that phi is automatically a symplectomorphism. Okay. So now, once you have this theorem, then you could make sense of what should a symplectic homeomorphism be. It should be the sort of limits you get here when you take the limit to be something non-smooth. Are there any questions about the theorem? I'm assuming almost everyone here has seen the theorem before. Okay, so definition, let phi be a homeomorphism of M. We say phi is symplectic if there exists a sequence of smooth maps, smooth symplectomorphisms, which converge to phi. Okay, and what the Eliashberg-Gromov theorem tells you is that if you have a phi, if you have a symplectic homeomorphism which is smooth, then it's an honest symplectomorphism. So the definition makes sense. And is that what it says?
Because phi could be smooth and have an inverse, C0 inverse, but not a smooth inverse. From what you just wrote. But maybe it's still a...
Right. I don't.
Maybe it's true that it's then it's inverse is still smooth.
Okay, so maybe it doesn't follow exactly from what I wrote, but it is true that if it has a smooth, if it's smooth, the inverse will be smooth too, I think. Okay, so
Doesn't matter.
yes.
If the derivative is 0, then simply should be on the linear level.
Yeah. So here's some notation. The set of symplectic homeomorphisms of M. So this is just notation. I mean, it's just you take the closure of symplectomorphisms. Here's closure. I'll just put C0 here. So with respect to C0 limits inside homeomorphisms. Okay, so these are symplectic homeomorphisms. In case you're wondering, looking for a class of examples, you could take M to be a surface. And in this case, the symplectic homeomorphisms of the would be a surface with an area form. The symplectic homeomorphisms are just area preserving homeomorphisms of M. So this is a big enough class of examples, and there's plenty there to play with. So these are symplectic homeomorphisms. I'm not going to say much about them, except that I thought I should give the definition before I tell you what Hamiltonian homeomorphisms are. I'll just say there's these have been studied fairly extensively over the past few years, and there's quite a bit of interesting stuff out there about these. But now that we know what symplectic homeomorphisms are, let's move on and see what Hamiltonian homeomorphisms are. And this is where the Arnold conjecture will come in. Let's recall something extremely basic. If you have a C infinity function, time-dependent function, or a Hamiltonian on M, then you could associate to it what's called a Hamiltonian vector field. So X sub h, it's defined, in this way. So if you plug it in the first component of symplectic form, you get the differential of the Hamiltonian. And if you take the flow of this, you get what's called a Hamiltonian flow. So here's my notation for it. And then the set of time one maps of such things is the set of all Hamiltonian diffeomorphisms. So these are all diffeomorphisms which can be reached via Hamiltonian flows. And this will feature later. So these are obviously, everybody knows these are symplectic diffeomorphisms of M. In fact, they form a normal subgroup inside symplectomorphisms. Okay, so here's a preliminary definition for what a Hamiltonian homeomorphism should be. You could just take the closure of Hamiltonian diffeomorphisms inside homeomorphisms of M. And people who work in two-dimensional dynamics, so people working on surfaces, have taken this definition, and they work with this definition. So if you read papers by, say, Le Calvez or Leroux or others, they take this to be the definition of Hamiltonian homeomorphisms. And they have proven there's a lot of very interesting results proven about these, and we'll see some of this come up later. But the problem with this definition is that once you go to dimension 4 and higher, there are no results out there. There's nothing that has been discovered so far, and I think the main result of this talk will tell you why there is no results about these things in dimensions higher than 2. So an alternate definition for Hamiltonian homeomorphisms, about which you could prove some things, and there's other motivations too, which I'll state, was suggested by Muller and O. And so here's a definition that I'll work with today. So let phi t be a continuous, so CTS means continuous, path in homeomorphisms of M, and I'll tell you what it means for this path to be a continuous Hamiltonian flow. So we say phi t is a continuous Hamiltonian flow if the following is true. If there exists sequence of smooth Hamiltonians such that, firstly, you might be able to guess this part, I'll want these flows, the smooth flows, to converge to my continuous flow. Okay, so I want to be able to approximate this continuous flow with smooth flows. And then the second thing that these guys thought of was that you have Hamiltonians to work with for smooth guys. Why don't we force this thing to have a Hamiltonian? And so what they did was say, assume that there exists a continuous function such that the HIs converge to H. And here's convergence with respect to the sup norm, say. So it's C0 convergence again. Okay, so in this way you get a continuous Hamiltonian flow with a Hamiltonian associated to it. Often you write phi t sub h for the path and the associated Hamiltonian, just to mimic the smooth notation. And then you could probably guess what the set of Hamiltonian homeomorphisms is going to be. Hame O of M is just a set of time one maps of such things. So it's a set of all homeomorphisms which can be reached as time one maps of such flows. And this is a normal subgroup of symplectic homeomorphisms.
Do you know continuous Hamiltonian which does not occur?
Yeah. If you take on the plane the absolute value of x, it won't have a flow in this. It's possible to prove that it doesn't have a flow in this sense. So if you take a sequence of smooth Hamiltonians which converge to absolute value of x, their flows will diverge. I think you need basically the energy capacity inequality to prove what I just said. So in fact, the set of, I'll give you an example. The set of Hamiltonians which occur in this way, it doesn't, in some ways it's large, but it also doesn't seem to be large enough in some sense. Like we don't know what kind of Hamiltonians can occur. Basically, I'll give you the only example I know. Take f to be a C infinity function, a C infinity Hamiltonian, and then psi to be a symplectic homeomorphism. Then the pullback of f composed with psi, so f composed with psi, pullback of f by psi, this is a Hamiltonian in the sense of this definition. It generates a flow. Its flow is what you would expect. Okay. And so these are the only examples I know of. Plus, take these and compose them with each other and take, these and the composition of these things. But that's kind of a rich enough set that you could prove interesting things. Some of these you'll see in a bit. So as I said, let me say a couple of words on what the motivation of Muller and O was for giving this definition. One motivation, as they said in their paper, is to develop a theory of continuous Hamiltonian dynamics. But I think so that was like a secondary motivation. But their primary motivation was to answer this question, which I think I stated in this room just a few weeks ago. So here's a question of Fathi. He asked, is the group of area preserving homeomorphisms of S2, is it a simple group or not? And so what Muller and O, so note that this is just the symplectic homeomorphisms of S2, as I think stated above. So Muller and O conjecture that these Hamiltonian homeomorphisms of S2 form a proper normal subgroup of area preserving homeomorphisms. Normality is obvious. Properness is what's very difficult to prove. And the same conjecture stands for D2, by the way. So this was really the motivation behind this. But OK, so that question's still open. Here are some. So now I'll state some results.
That conjecture.
Kind of. I also.
So that he doesn't read the proof something.
Yes. I want to say it seems like a lot of people believed. You also believe this conjecture, all right? Or a lot of people have, or think there is like, let's say 90%, 80% chance that this is true, but 90% we saw last week doesn't mean a few weeks ago we saw it means nothing, and it could lead to this. Yes, the exact opposite could come true. So I think a lot of people believe that this is true. Okay, so now I'll state some results about these Hamiltonian homeomorphisms that that show that these things are somewhat nicely that behave somewhat nicely. So one result is this. Here's a question that some of you might have in your mind already: uniqueness. If you have a smooth, if this object is smooth, then the Hamiltonian, the H, uniquely determines its flow, and the flow determines the Hamiltonian up to a constant. And the same thing is not so obvious for these continuous Hamiltonians. So the uniqueness theorem says if you have two continuous Hamiltonian flows which coincide, then these two differ by constant. Okay? And so this was first proven by Claude, and then later on Buhovsky and myself gave a different proof of this as well. So in the same paper, the statement I made about absolute value of x not having a flow, it follows from slight strengthening of this theorem. And to prove this theorem, you need the energy capacity inequality. So that's why I said you need energy capacity inequality to show there are Hamiltonians without flows. Okay, so the fact that the uniqueness theorem is true is kind of tells me that this definition passes like the first test of sanity, because if this wasn't true, then then I don't know what we would do with these things. I mean, you'd better have at least some nice properties. So actually, I should correct myself. This direction was proven by Viterbo and Boavsky and myself, and then this other direction was proven by Muller and O in their original paper. So this was the uniqueness of the Hamiltonian is what remained open. Here is another interesting property that these guys have. So let's recall. I'll say a submanifold of a symplectic manifold is coisotropic. Everybody knows what that is, but if the symplectic orthogonal to each tangent space is contained in the tangent space itself for all p. Okay. So examples, hypersurfaces and Lagrangians. And so the set of symplectic orthogonals to the tangent spaces is an integrable distribution, is integrable. So it gives what's called the characteristic foliation of C, which I'll denote by curly F. Now, suppose you have a smooth Hamiltonian on your symplectic manifold, which is constant on some coisotropic. So H restricted to our coisotropic is constant. But constant, again, I mean a constant that just depends, function that just depends on time. Then note that the differential of H restricted to the coisotropic will be 0. And the differential, I mean, this is just saying this thing is 0, restricted to C. So xh is in the kernel of omega, and that tells you that the Hamiltonian vector field is in the symplectic orthogonal to the tangent spaces, right? So, and this tells you that if you look at the flow of this Hamiltonian, it not only does it preserve the coisotropic, it flows along the leaves of the foliation. The flow is tangent to the leaves of the foliation. Of course, everybody has seen this. If C is the hypersurface and you have a function that's constant on it, then it flows along the characteristics of the hypersurface. And this can be reversed. Okay, so this is something that's true for smooth Hamiltonians. And then one question you could ask is that, is it true for continuous Hamiltonians? And so the next theorem I want to tell you about without proving it, and this was joined with Vincent Moulière and Rémi Leclerc. Is that the same thing is true for continuous Hamiltonians. Okay, so but this time I'm assuming phi th is a continuous Hamiltonian flow. Okay, so to me these two results, especially this one tells me that these continuous Hamiltonian flows inherit a lot of properties of their smooth counterparts. So having seen these results, I was at least half convinced. I was giving it like a 55% chance that something like the Arnold conjecture should be true. And there are some other results that convinced me that there was an 80% chance it was true. So I'll state those results in a second. So knowing these, we were kind of convinced that the Arnold conjecture was true, but it's not true. So let's talk about. So now I'll tell you the statement of the main result of the talk. So here's this C0 Arnold conjecture, and the statement should be that if you have a closed symplectic manifold, then the number of fixed points of phi is less than or equal to crit of m, which I already defined, the minimal number of critical points of a function on m for all Hamiltonian homeomorphisms. Okay, so here's a theorem by, okay, so this is why I was 80% convinced the Arnold conjecture would have to be true. Franks, Matsumoto, and I mean, there are other proofs of this now too. These are the two guys who proved it first, but now there's an interesting proof with Lecalvez as well, who proved that number of fixed points of phi is true. I mean, the Arnold conjecture is true on surfaces. In fact, not just for Hamiltonian homeomorphisms, but for their definition of Hamiltonian homeomorphisms. So we're looking at the closure of Ham-side homeomorphisms, where M here is supposed to be a surface. So this statement says, if you got a sphere, every Hamiltonian homeomorphism has at least 2 fixed points, and for other surfaces, you get at least 3 fixed points. Okay, so what about dimensions 4 and higher? The first, let me make a remark. The number of fixed points of a Hamiltonian homeomorphism is at least 1. And this is by floor theory. Right, because every Hamiltonian diffeomorphism has so many fixed points, or at least non-degenerate ones for which we know the floor Arnold conjecture is true. And you could write a Hamiltonian homeomorphism as a C0 limit of Hamiltonian diffeomorphisms. So if you have a sequence of maps which have fixed points and they converge to another map, the map will have a fixed point. Okay, so this much we know. And so we tried, well, when we first started thinking about this, knowing these results and also the result of Franks and Matsumoto, we tried to show at least, there are some number of fixed points, let's say 2. But every time we tried to prove this thing, there was we could see no obstruction from all the fixed points collapsing into 1. You could write this as a limit of smooth Hamiltonian diffeomorphisms, which have many fixed points, but you could see no obstruction from saying all those fixed points would collapse into 1 in the limit. And so you could guess what the main theorem is. So here's the main theorem of the talk. And this is with Lev Bohovsky and Vincent Milliard. If the dimension of M is at least 4, then there exists a Hamiltonian homeomorphism such that this homeomorphism has exactly 1 fixed point. Okay, so right, so the worst case scenario is actually true. I mean, things couldn't get worse than this, but okay. So the Arnold conjecture is false, and then sometimes people say, okay, maybe a variant of the Arnold conjecture is true, but they all predict more fixed points than 1. And then sometimes people say, okay, maybe you should define crit of m to be the number of critical points of a continuous function. Well, whatever that's going to be, there's a max and a min, so there's always 2 at least. So okay. It seems, at least at this stage, it seems like there is no hope of rescuing the Arnold conjecture. There's some things I got to say now. Okay, so there's more to the statement of the theorem. Okay, so the situation looks bad, but actually you'll see that it gets even worse. So here's, furthermore, the following 2 statements are also true. Furthermore, so first thing I want to say is that let P be the unique fixed point of phi. So we can arrange such that phi is a smooth symplectic morphism on the complement. So it's a symplectic diffeo here. I mean, you'd expect that if you have a counterexample to the Arnold conjecture, it better be non-smooth. But okay, so you could concentrate all this non-smoothness at that single fixed point.
Can you compute some local invariant near that point? There must be something.
There's, I mean, you could talk about. That's what I was going to say. You could probably talk about local floor homology for this one.
Yeah, it should be.
I mean, you could associate kind of like a barcode or spectral invariance or something like this, which is the same thing as saying there. Well, that's more like a global invariant, but I think you should be able to define a local floor homology for this fixed point, but it's to be seen.
Is there a way to say that counted with some multiplicity that you get more than one? Should be.
Yes, so what happens is that, okay, so now that you asked, okay, so there's this, here's another interesting thing about this phi, or, this phi is a homeomorphism, is a Hamiltonian homeomorphism with a Hamiltonian. And once it has a continuous Hamiltonian, you could talk about spectral invariance for the continuous Hamiltonian. So let's say phi or its Hamiltonian. Phi has, I think, crit of m distinct spectral invariance. So maybe that gives a bit of an answer to your question. So although there is only one fixed point, but this homeomorphism, the generating Hamiltonian has many, many distinct spectral invariants. So if you count the number of spectral invariants, then the Arnold conjecture is satisfied.
So maybe we shouldn't just count critical form.
Yes. Yeah. Indeed. I'll say something about that in a few minutes, actually. And then there's one other thing I was going to say. So this example just looks more and more bizarre. But here's one other thing that could go wrong. Okay, another thing that you might say is that, okay, this closure of Ham turned out to be a bad definition for Hamiltonian homeomorphisms because you couldn't prove anything for it. Now we pass to this subset, this something that's more restrictive, and it turns out you can't prove any. Okay, you could prove some interesting things over there, but you can't prove any. There's no fixed point theory for these guys either. So you might have the idea. You might suggest that maybe you could restrict even more, change the definition of Hamiltonian homeomorphisms, work with something better that could possibly produce, a fixed point theory. Maybe our Arnold conjecture will be true for some homeomorphisms. And the point of the next remark is that you can't do that either. So I always confuse my audience when I state this. So let's see if I could do it this time. It's very easy, but I don't know why I messed it up. So let G be a candidate for your favorite definition of Hamiltonian homeos. Right? So this is the set of all Hamiltonian homeomorphisms whatever, you have a definition of Hamiltonian homomorphisms, let G be the set of all such things. Let's assume that G, I mean, if you have a definition of Hamiltonian homeomorphisms, it better count all Hamiltonian diffeomorphisms as Hamiltonian homeomorphisms. And let's suppose that it's a normal subgroup of symplectic homeomorphisms. So is it still here? Right. So Ham is a normal subgroup of Simp. So if we require that your candidate group of Hamiltonian homeomorphisms is a normal subgroup, then I can put phi in there. Then exists phi in G with number of fixed points of phi just 1. Okay, so that's okay. So this is the full statement of the theorem. Maybe if there are no questions, maybe I'll. Oh no! Are there no questions about the statement? So maybe I'll say something about. Here's a remark or something that's work in progress that kind of gives an answer to the questions that Helmut and Claude were bringing up. So theorem.
Question for you.
Yeah.
So does this theorem, is that what you were referring to earlier when you said that with the original definition of Hamio, there are no results in dimensions 4 and higher?
I mean, no, when I said there are, so the original definition of what I presented as a preliminary definition of Hamio was just take the closure of Hamiltonian diffeomorphisms, right? And what I was saying is that there are just no known results for those things. And it turns out, I mean, this kind of gives an explanation why there are no known results for at least because this is contained inside there. So this tells you why there is no fixed point theory if you look at closure of Ham, or if you look at this thing, which is supposed to be nicer than the closure of Ham. So does that answer your question? Or?
Yeah. So you specifically meant that this explains why there are no fixed point results.
Right. Yes, there are no fixed point results on the closure of Ham or Hamio or anything that satisfies this. Except that now I'll state a fixed point result for hamiomorphisms.
But that's not totally convincing because also for Hamio you don't have any fixed points, but still you have interesting results.
Right. So
it could be the same for Hamio.
right. There could be when I said there are no results, maybe I should have. Well, maybe there are. I don't know of any results. There might be interesting results, but there's no. You can't prove anything about fixed points of them. Except that maybe you can, because now I'm going to state something about fixed points of. Okay, I take that statement back. Okay, so here's the next theorem, or this is like a 90% theorem, so it might turn out to be completely false, and this is also joined with Boavsky, Homolier, Seyfaddini. I'd say this is more likely to be true than all those predictions about the election results. So that's an obvious. That's an obvious obviously true statement. No. So the statement is this.
Ignore the context.
Yeah. Okay. So here's the statement. Let phi 1 H be a Hamiltonian homeomorphism. So once you have a Hamiltonian, you could talk about spectral invariance associated to H, but somehow you can't talk in dimensions higher than 2. You can't talk about spectral invariance of the homeomorphism. You need the Hamiltonian. So here's what we can actually prove. If the number of spectral invariance of H is less than the number of critical points of M. Oh, no, less than, cup length of M. then the set of fixed points of phi has non-trivial homology. So this is to have non-trivial homology. I mean,
As a set?
if you take a neighborhood of this and include it, you look at, so what I mean is precisely this. Take U.
And the same like several minimum factorizations are the same.
Right.
Has non-trivial homology as a set?
Yes. So I can say a precise statement here. You take a neighborhood of the fixed point set, take any open neighborhood of the fixed point set and take its inclusion into M.
Okay.
Then it induces a non-trivial map on homology. So not only is it infinite, but it's, you know, for example, it can't be a contractible circle or something like that. So this, I mean, I think this sort of statements are kind of known in the smooth setting.
Yes.
This comes from Lusternik-Schneiderman theory. And you know, the same sort of proofs, you can make it go through. So this can be reinterpreted as some version of the Arnold conjecture that's true for these guys. That if you find something that has too few
But what is the assumption on M?
just closed, and you can define spectral invariance on it.
So that
Oh, sorry.
because
Sorry.
yeah, okay.
Aspherical. Right, because I don't think this is true in the smooth setting if it's not
No,
aspherical.
Then we don't even know. I mean, there are not good minimum factorizations. There's no good list. I mean, nobody came up with a good list of neurons. And there are no assumptions.
Yeah. Okay. So if you take H to be smooth, then this implies the Arnold conjecture in the smooth setting. It just says either you have infinitely many fixed points, homeomorphism, or the number of spectral invariants is bigger than the cup length, and for each spectral invariant you have at least one fixed point. But in the C0 setting, the number of spectral invariants doesn't tell you anything about the actual number of fixed points. So this is the sort of statement that seems to survive.
So what does it mean for fixed points to have several spectral invariants?
So, I don't really know what I mean. I just mean that what I mean.
That's what it means, because if you have
Right.
only one
Oh, yeah. I can't make that statement precise right now. I hope to be able to do it in the future. But for example, when you have just one fixed point, then all the spectral invariants of the Hamiltonian are concentrated at that fixed point. So,
Yeah, but what does it say about the fixed point itself? Is there some?
not sure. I mean,
It says that either some area goes to it. So spectral invariance you can define by the smooth case by taking arcs from one
Right.
to the other and then looking at, imagine one of fixed point you keep at infinity somewhere.
right.
You take
So
path
you think-
from your fixed point to the point at infinity, look at the image and look at the
Yeah.
area that's enclosed.
Right.
So this probably means that such an area is not defined. So
Right. Yeah. I mean,
does it mean this area is infinite or something like that? Or
I just think you can't. It means you can't really define the. One of the things it means is that you can't define the action of like a periodic orbit, for example. Just
yeah, something like that.
yeah, but I don't know how to make that statement more precise. Okay, so if there are no other questions, I'll try to sketch the proof of this theorem, the counterexample. So if you could make sense of local floor homology for these fixed points, then maybe you could say something interesting about what it means to have several. I mean, these questions are all related. How many, if you have several spectral invariants concentrated at one fixed point. Okay, so here is the proof, or sketch of the proof. So the first step is to do the following. Step 1. Construct a Hamiltonian homeomorphism with the following properties. There exist a tree T inside M, this is just a subset of the manifold M, with the property that so the first property this tree has is that all the fixed points of this homeomorphism are on T. In fact, they're vertices of the tree. But the important thing is that they're contained inside this set, the tree as a set. The second thing is that the set T, the tree, is invariant for the homeomorphism. Okay? And the third property is that this homeomorphism is smooth. So it preserves the tree T, which means it preserves the complement of the tree. So it's smooth in the complement. Is a symplectic diffeol in the complement. And so this last thing will be used to show, whatever I get in the end will be smooth everywhere except at that fixed point. Okay? And so this is the step where most of the hard work is concentrated. So first you need dimension of M to be larger than 4 to construct this in the construction of this tree. And then second thing is that I don't think this tree could exist if you had if psi was smooth. So this is already, you need to go outside the smooth category to construct this tree. And to see why the tree could not exist for a smooth guy is that, suppose, here's an edge of the tree and you got two fixed points. So the edge of the tree is invariant, which means that the action of the two fixed points should be the same. So if the actions of, which would tell you all the fixed points of this, if it was a diffeomorphism, all the fixed points of the diffeomorphism would have the same action, which is not possible because you have at least two distinct spectral invariants. Okay, so this is where you need both four-dimensionality and you need to go outside the smooth category. The next step is, so once you have this tree, you collapse it to a point. So here's the second step. So let's fix a point P on our manifold. This is going to be the eventual fixed point. What I'll do is I'll build a sequence of symplectomorphisms with the following property. So firstly, these eta i's will be convergent in C0 topology to some map eta. And secondly, eta will have the property that it collapses a tree to the point P. Okay, so this map is not one-to-one. So in particular, it can't be a diffeomorphism. So I get a bunch of maps, a symplectic diffeomorphism that converges to some map that has this property. And again, to get things to be smooth on the complement of that fixed point, you could arrange that eta. So it sends T to P. It sends the complement of T then to the complement of the point P. And it will be a symplectic diffeo here. And at this point, you probably can see what you need to do to construct a counterexample. Here's how it works. So let me put it in a nice diagram here. So here's M minus P. Well, M minus So look at the map, eta, psi, eta inverse. Right? I mean, it sits in this nice diagram. This map is fixed point free. Right? This was the point of the invariant tree, because I put all the fixed points of this map psi on T. So on the complement, there are no fixed points. So that tells you this map is fixed point free. So these two maps have no fixed points. Okay, so now I've constructed a map eta psi eta inverse, which is fixed point free on the complement of the point P. So I'll extend it to the point P by just saying it's, define phi. My counterexample will be defined in this way. It's eta psi eta inverse on the complement of the point P. So here it has no fixed points, and at P is P. Okay, so there you go. You get a map with just one fixed point. And now, of course, we need to show that this is actually a Hamiltonian homeomorphism. And I won't prove this, but you could show, what we do is we show that the sequence eta I psi eta I inverse, so this sequence of conjugations, converges uniformly to phi. Okay? And so this is despite the fact that, look, so these eta i's, they C0 converge to a map which is not a homeomorphism. So they have to diverge. So this sequence diverges. Well, diverges. But despite the fact that these eta i's diverge, the sequence of conjugations converges. And this convergence is because this is where you use psi preserves the treaty. So if you just try, so this is where the invariance of the tree is used. So if you just were to try, take a bunch of fixed points and try to bring them together and collapse them to one fixed point, which is what you do via a sequence of maps conjugations, which bring these points closer and closer. If these fixed points are not sitting on an invariant tree or something invariant like that, then the sequence of conjugations will diverge, and you won't have a homeomorphism in the limit. So that's why you need to build this invariant tree. So clearly this phi is in the closure of Hamiltonian homeomorphisms. And then there is a next step, which I won't say anything about. Step 3 is you turn phi into a Hamiltonian homeomorphism. So you play some tricks, and it turns into a Hamil.
That means turn.
Turn it.
Show that. That's what you mean. Because phi is already given.
Actually, so we modify it. Modify. Wait. You could do both. You could modify it or show it's one of these. So if you want to show it's a Hamiltonian homeomorphism in the sense of that definition, what you could do is go through all these steps, and at each step make sure that your Hamiltonians also converge and you have control. In all these steps that I said so far, you need C0 control on the time 1 maps. Now you go repeat the same story, but making sure you have control, C0 control on the Hamiltonians too. So then you can guarantee this will happen. So there is extra work to show that it has a Hamiltonian. So there's just enough time to sketch either the idea of step 1 or step 2, and Egor, who's not here, asked me to this time sketch the proof of, he had seen the sketch of the step 2, so I'll sketch the proof of step 1 for Egor, who will watch it online later. Okay. So I don't think I'll get too far, but I'll try to say what the main ideas behind the construction of this invariant tree are. Okay, so back to step 1. How do you construct this invariant tree? So there is a key lemma, which I'll just state, but won't prove. And this is what Bohovsky and Opstein call quantitative H principles. So they have a paper on quantitative H principles, and this is an example of one such thing. So here's the key lemma. Suppose you have two curves in R2n. Let's say they look like this. I mean, here's gamma 0, and here's gamma 1. And I'm going to assume that the area between the two curves is 0. So assume integral of x dy over gamma 1 is equal to integral of x dy over gamma 0. Let's call these points P and Q. Then, it's a standard fact that everybody knows. If this is true, there exists a Hamiltonian flow such that this flow fixes the endpoints of the curve and sends, at time 1, sends one curve to the other curve. Okay, that's an old fact, but here's what makes it a quantitative H principle. Suppose gamma 1 is C0 close to gamma 0. Then what you could do is make sure that the whole isotopy is C0 close to identity. C0 small. Small. Okay? So if this point is, that lemma before this part, it could have been that this point, which is close to here, it could have ended up over here. That would produce a large isotopy. But since we need C0 control, you prove a lemma that says, you could actually find an isotopy that sends this point, which is close to here, exactly to there, or close by. So this is not a very difficult quantitative H principle to prove. I think it's a very believable statement. And it's true in dimension 4 and higher. So here, R2n, n greater than or equal to 2. So by the way, this first step is, as I said, is the only step where we use 4-dimensionality. So if you could produce that invariant tree on surfaces, then you could repeat all of these other things and get a counterexample to the Arnold conjecture on surfaces too. So this is one of the things, construction of a tree is exactly what fails in higher dimensions. How much time do I have left?
5 minutes.
Oh, okay. Okay, so here is what I'll do, is I'll show you how to construct one edge of the tree. So let's pick F to be C2 small Morse. And P and Q to be two critical points of F. And what I'll do for you is I will construct a Hamiltonian homeomorphism, or just something in the closure of Ham, so we won't prove that, and a curve gamma from R to M such that at the two ends, so if you compactify it, you get a compact arc from P to Q, the two critical points of F, and additionally it has this property. Can people see this board? It says psi at gamma of t is gamma t plus 1. So gamma is an invariant curve for psi, and furthermore, psi will be C0 close to phi 1f. So this is the distance between the two is C0 is small, and fixed points of psi. In doing so, I will create no new fixed points. Of course, the reason I need this C0 control is that I want to make small enough perturbation so that I don't create any fixed points while I create this gamma. Because if I create new fixed points, then I'm in trouble. So how does that work? So suppose P is here. So here's a picture. P is here. I'll put Q over here. And I'll assume that P is not, is not an elliptic fixed point. So let's assume I can find a point, say, X on its unstable manifold. So assume it's not like a maximum of the maximum or minimum. So you could find a trajectory of f that goes from P to some point X. And I'll assume you can find the trajectory of y, a point y that's on the ascending submanifold of Q. So I'm making these assumptions. And here's one more assumption that I'll make. I'll assume there exists a curve alpha that looks like this. So this is, f is the height function, and I have, x sits above y in height, and f composed with alpha is decreasing. So the picture I want you to have in mind is maybe this. Here's P, here's Q, and what I've drawn here is like you go to X, there's this, go to Y, it's this way, and then I have this alpha here. So that invariant curve gamma that I'm going to build, the first part of it is here, the last part is here, and now I've got to fill in the space in between. Here's how you start doing it. Let's start flowing from X by time, for time 1. So I get to here, and then I flow again. And it would be wonderful if I could just go around and eventually come and end up at Y. Obviously, that's not going to happen because these are on two, at least one reason to see it is that these are on two different level sets. But if I assume X is a recurrent point of my flow, I will eventually come back very close to this curve. I'll come back close to this green curve, which is kind of like a guiding curve. Once I come back to here, I'll make a jump from this point to a point which I'll call x1, so this is x0, and then I repeat the same process. So this is phi2f, phi1f of x1, and so on. And then it will come back again. I'll pick x1 to be recurrent, so I'll come back again, and I'll do this again. And eventually, I'll get close to some point here, which is very close, and then I'll jump here. So I've got these, let's call this y0. So I've got these curves, which, these line segments, each of which is kind of invariant in the sense that if I map one of these points by phi1f, I'll end up on it, except this chunk where it just goes nowhere. Now the goal is to glue these curves to something that will become invariant for a deformation of phi1f. And let's focus on this patch here, and I'll tell you how to do it. So the first step is easy. Let's at least make sure these points are sent to the right points. So I'll pick a small Hamiltonian diffeomorphism, which I'll call tau 0, which maps this point to this point. Here's tau 1, and here is, like, if this is yn, tau n does this. So I'm going to now draw this picture over here, and we'll zoom on what happens. So this was y0, x1, and then I had a map tau, which sent y0 to this point. So if I apply tau to this line segment, then the image will look something like this. Okay, so by doing this, by applying these taus, I glued this part of the curve to this part. So wait, I'll let tau be the composition of all these things. And then psi1, so the first step of the modification is to look at, let psi1 be this. Now, if you apply psi1 to this curve here, it won't land in the right place.
Do you assume you're not perturbing the other ones?
Which other ones? So I'm perturbing all of these at the same time. So there's tau 0, tau 1, tau n.
Yeah, but the support of the are so somehow disjoint.
Yes. So these are very small. Like this point is so close that I could pick the supports to be disjoint at this point. This is not where problem arises. So that sort of problem arises in this next step. So let's call this curve, so what starts here and ends here, gamma 0. And I'll call this one gamma 1. And if you look at the image of, look at psi 1 of gamma 0, this is what you get. It looks like this. I mean, I could get it to coincide with this near the endpoints, and it will be a curve like that. So you just have to check what psi 1 does to this curve. It will just shift it over like this. And kind of, well, it's easy to check that. OK, now I want to construct eta 1 that sends this curve to this curve. And here's what I do. I'll pick a homotopy between these two curves. So first there's an obstruction, but I'll ignore the obstruction. This curve might not have the same action as this curve. I mean, this is in a small chart. This is taking place. If I want to find a Hamiltonian diffeomorphism that sends this to this, I need to make sure the two have the same action. Otherwise, it won't. There's an obstruction. But let's just ignore that part for the time being and worry about the other things. So what I'll do is, let's assume the two have the same action. Then I'll pick a homotopy, so a surface that kind of a homotopy from this curve to this curve. And I'll find eta 1, something that's supported very close to the homotopy that maps this top curve to the bottom curve. And now you have to worry whether the support of this intersects other parts of the curve. But you could ensure that that doesn't happen because this is a surface and the rest is a curve, and you're in dimension 4. So by general position argument, this surface is disjoint from the rest of the curve, and therefore you could find, you could make sure this eta 1 doesn't interfere with what you've done before. So find eta 1 such that eta 1 of psi 1 of gamma 0 is gamma 1. But I also want eta 1 to be C0 close to identity, so you use by lemma. I apply that quantitative H principle to find something that's C0 small. Because if it's not C0 small, you might have created a new fixed point. But if it's sufficiently C0 small, then composing something that doesn't have a fixed point in some region with something that's C0 small doesn't create any new fixed points. And so I get this eta 1, and then I get one for each of these regions. Then I repeat this down here, and so on. And then I'll let psi be, so you might be tempted to say let it be eta 1 composed with eta 2 and so on, but that doesn't work. So you let it be eta even, the composition of the even ones, with the composition of the odd ones, and then with psi 1. And then that produces something that has an invariant curve. The reason for this is the support of eta 1 might intersect the support of eta 2. And if you want to have something that's C0 small in the end, then there's many of these, so you'd have to add many small epsilons and get something large. So to keep it small, you compose the even and odd ones, because the even ones or the odd ones, they have, this is disjoint from this one. So this is C0 small, and this is C0 small. And so you get something, an invariant curve. OK, then there's some problems to take care of, like the fact that these two didn't have the same action. So then you come back. You make a C0 small perturbation where you're using 4-dimensionality again to adjust the action. And then you could do this. And then you have to carry these action adjustments all the way to the end. And these action adjustments will go all the way to here. There will be many action adjustments close to Q, and that's where you get actually the non-smoothness of the curve and the homeomorphism. I've gone, I think, 5 minutes over the 5 minutes. I'll stop here. Thanks.